we have realized now that how to what is meant by space vector PWM, that we have understood, and then we have slowly moved on to understand how we can realize a voltage when it is seen as a vector for a multi-phase system. So this is how we have discrete voltage vectors when we are applying the voltage from an inverter. So particularly for 2-level 3-phase inverter, we have 8 vectors, out of which 6 are having some magnitude and they are located at different locations. So these are called active vectors, and 2 do not result into any output voltage. That means the output voltage given by the 2 vector states or inverter states are 0. That's why these are called 0 vectors. This we have understood. Now we are trying to realize our voltage vector which we need to apply on the motor in terms of these active and 0 vectors. So first we have seen that any other PWM technique, for example 6-step or sine triangle, these are also basically applying somehow one of these active vectors or 0 vectors to ultimately that's the option to realize the average value of the voltage, whether in terms of per phase or in terms of the voltage vector. But effectively the point is that some voltage vector is applied at any given point. Now we have understood that if we need to do the same thing in terms of a space vector, which means we are not worried about what is our carrier and how our modulating signals are, but we know that we have some voltage vector which we want to realize, and it is located in a sector. Let us say sector 1 I take for example. It is located at some angle gamma. So what we need to do, basically we need to apply the voltage vectors 1, 2, 0 and 7 in certain sequence and for certain time duration. So first we are trying to see what is the time duration for which we need to apply these vectors. So T1 and T2 are the time intervals or dwell times related with the vector 1 and vector 2 respectively. So what we are seeing that these T1, T2 can be solved in terms of the magnitude of the voltage vector which you are trying to realize and its location, which means the angle gamma. So if we have T1 and T2, for maintaining a fixed switching frequency or maintaining a fixed sampling frequency, we need to have a fixed TS. That means TZ is basically difference of TS and the sum of the active vector angles, active vector times, dwell times. So this is what we have done, and now we are trying to realize how many samples we should have. Let us say gamma angle is given, but how to choose this gamma? First question is that. So in terms of how many samples and location, these two things are important now. So first of all, how many samples? We need to know how many such discrete vectors should be there within a sector. I'm talking about a sector because many things we can generalize in terms of just one sector. So I will come to that later on. Now what we are seeing over here, that number of samples can be basically correlated to what switching frequency we are looking at. So definitely we are trying to have a PWM for a given switching frequency, and that is what relates and decides everything else. So first let us see that in one sample what is happening. We are basically, let's say, applying first a 0 vector, say 7, then this 2, 1 and 0. बाद में आएंगे. So we have 3 switchings basically happening in one sample. Next again we have, let's say, the other sequence if we take 0, 1 to 7. So again we have 3 switchings happening in one sample. So each sample is basically relating to 3 switchings. It is switching, not switching cycle. So which means only going from either on to off or off to on. This is not a complete cycle I am talking about. Number of switchings I am talking about. Now we know that our switching frequency must be, this ratio of switching frequency and the fundamental frequency must be an odd number. So which means the options what we have, we may have 1, 3, 5, 7, 9, 11, so on as our pulse number. These are the conditions on the pulse number. Now, because it is happening as multiple of 3, every sample we have 3 switchings, so we can realize only these numbers. 3, 9, 15, 21 using the conventional space vector PWM. So when I say conventional, the meaning is that we are having T1, T2, these dwell times, and Tz dwell time divided by 2 for the two zero vectors. I will come to that. But as of now, just remember that we are talking about something called as conventional space vector PWM. So here we have all four states applied, which are there in this sector. All four states are being applied for a given sample. So the options for switching frequency are, or for the pulse number are 3, 9, 15 and 21 and so on. We can go in this manner. Now, if this is the condition, then we can define how many samples should be there in one sector. So let's say if we have pulse number equal to 3, how many samples could be there in one sector? Okay, another thing we need to know here before going to that, this is 3 switching happening for all 3 phases, right? This is not for just one phase. Pulse number we are defining for one phase. This is per phase. Pulse number P is related to each phase, correct? Which means the total number of switchings happening in the complete 6 sectors. The complete circle, if you form over here, there will be 6 sectors, and all the places there will be some switching happening. Now we are trying to correlate with that. So if the pulse number is 3, basically what it means that there are these many number of switchings happening. Correct? Yes or no?
Yes, sir.
Okay, little louder you need to speak.
Sir, no, sir, didn't get this.
Okay, this is now you understand by switching frequency, right? What is switching frequency? How many times
Yes,
the device is going from one state to another and then coming back to the same state. This is one switching cycle. Now, how many times this is happening per second? That is what is your switching frequency, right?
Yes, sir.
We have correlated this switching frequency with our fundamental frequency through another term which is called pulse number. This is clear to all of you?
Yes.
Yes,
Correct? Which means if the pulse number is P, let's not go for any number as of now. Let's say the pulse number is P. Then how many switchings are happening per phase? Switching meaning 1, 2. These are 2 switchings per switching cycle. Understand the difference between switching cycle and switchings, right?
Yes, sir.
This is switching cycle, and there are 2 switchings in each switching cycle. So if P is the pulse number, how many switchings will happen per phase? 2 into P, right?
Yes, sir.
This point is clear to all of you?
yes, sir.
Fine. Everyone is
Yes,
clear
sir.
here? What is meaning of this 2 into P? This is total number of switchings happening in a given phase for a pulse number P. Fine. Now, how many phases are there?
3 phases.
3 phases.
3. So total number of switchings would be into 3 for all 3 phases. Any confusion in this? Any confusion in this one? Fine. This is
Yes,
total
sir.
number of switching which will happen in all 3 phases for a given pulse number P. Any confusion in this point?
No, sir.
Correct. Now we have 6 sectors. No, we have divided the whole circle in terms of 6 sectors. Okay, I can bring that here for clarity. So when I say total number of switching is 2 into P into 3, basically this is happening in all 6 sectors. And of course, we are talking about same number of switching in all these sectors, right? It cannot happen that one sector is having more switching, another sector is having less switching. Or a symmetrical, like a normal space vector PWM or conventional space vector PWM. This is what is required, or this is what is expected. Now, if this is the total number of switching happening in all 6 sectors, what will be the number of switchings per sector? That should be divided by 6, isn't it?
Yes, sir.
Correct? If total number of switching in all these 6 sectors are 2 into P into 3, then for each sector, there are basically this whole divided by 6. That many number of switchings happening in each sector, which means basically in each sector we have P number of switchings happening. Fine. This point is very clear to you, right? How pulse number is related to number of switchings in a given sector. Right?
Yes, sir.
Yes or no? Clearly, you tell if there is any confusion, immediately tell me. Clear to all of you?
Yes, sir.
Okay, now I go one more step. Now I am saying that for each sample, how many switchings are there?
For 3.
Three. Which means if we want to have P number of switchings per sector, how many samples should be there in one sector? Simple question. We want to have P number of switchings in the sector. So we are trying to compute how many samples should be there. Each sample is giving me 3 switchings. How many samples should be there? Okay.
Sir, 3 into P.
3P, sir.
See, this is what? What is this number? Tell me again.
Sir, pulse number.
That's okay. Pulse number, what other thing we have related to?
So number of switchings per sector.
Per sector. So number of switchings per sector is P. Say P equals 3. Correct? Now we are trying to say that how many samples should be taken to realize total number of these switchings. P equal to 3. How many samples should be taken?
Sir, 1.
How is it coming? P divided by 3.
3 by 3. Yes, sir.
So each sample, how many switchings you are getting?
3.
3. So that means number of switching per sector. If you write in terms of number of samples, it will be this. Number of samples in a sector into 3 will be your total number of switching happening, and which is basically your pulse number P. Are you able to correlate this? Fine.
Sir, yes, sir. But like in general, like when we are comparing per phase analysis, like we generally see for only one of the waveforms, right? Like all the 3 we don't consider.
But here we have to consider, no, this is space vector. That's why I said in the beginning, this is cumulative effect. We are not bothered about just one phase. We are seeing the cumulative effect of all. So we have to talk about all the phases together. Per phase analysis we have left behind. Fine?
Yes, sir.
Any confusion here?
Yes, sir.
Yes or no? Say quickly.
No, sir.
No, sir.
Okay, now if there is no further confusion, then let me ask questions. Okay, if I say that my pulse number is 3, how many samples should be there in one sector?
Sir, 1.
1. If I say my pulse number is 9, how many samples should be there in a sector?
3.
3.
3.
3.
Similarly, for 15, there should be 5.
5. Yes.
For 21, there should be 7. You see, all odd numbers are appearing over here. And because each sample is associated with 3 switching, we are getting switching frequency which is of the order of odd triplet number. Understanding my point? This is for conventional space vector PWM, and I'm again emphasizing on this point. Tomorrow we will see if we have some other space vector PWM, how this can be different. It's not necessary for all space vector PWM techniques. This is true for only conventional space vector PWM. Fine. Now here, when we have understood that this should be the number of samples in each sector, which means if we say that, okay, for pulse number 3, if I want to locate my samples or just to visualize how it will look like, so there should be one sample in each sector, which means say here, here, then here, then here, then here, and here. This is how total samples will look like for pulse number 3. Total number of samples in the complete space vector. That is all. So what you have basically one particular gamma and one particular value of Vs to realize this within a sector. There is no other number. It's a fixed number. So if someone says that P equals 3, you would know that, okay, what I'm trying to realize. No further information is needed. Now the question comes, okay, there should be one sample within this, but where it should be? My gamma can vary between 0 and 60 degree. So to differentiate, let me write as gamma 1 because there is only one sample. So what should be the value of this gamma 1?
30
Can it be
degrees.
0 degree? Can it be 60 degree? Can it be 20 degree? Why 30 degree?
So we are taking only one sample. So
why 30 degree? Question is that. Why not 25 degree? Why not 40 degree?
Sir, like it looks symmetrical, like if we draw.
Okay, let me draw it symmetrically. Okay, I'm taking samples here. Is it not symmetrical?
Yes, sir, it is symmetrical.
What's the problem in this?
sir, per sector, we have to take only one sample. So to realize,
I have taken one here. This means for the next sector.
sir, but it is
Okay, I will slightly change this.
So the
It
error
will
will be
have,
more.
huh?
Error will be more.
Which error?
Sir,
Let's say I'm taking sectors, this samples here. Which error you are talking about?
sir, the difference between the tip of the one direction.
Think and tell.
sir, we have to realize for the whole 60 degrees. So each vector. So to minimize the error, we
Which
take.
error are you talking about?
Sir,
Sir,
as a vector, yes, sir.
like the reference vector that is being generated and the actual one that we require.
So can I not generate a vector over here at this location in this sector?
Sir, no, sir. Like it will depend on the like what we want to generate. Suppose
Yeah,
that
I
that
want to
vector
generate
can be
this.
anywhere in the sector.
So I am keeping it here. Let's say at 10 degree. What is the problem? My question is that Okay. A more fundamental question, which will basically connect to what Ashish is saying and what you are trying to say in terms of error. I have to realize a vector over here in this sector. Say, is it compulsory that I have to use these two vectors only? Can I not use vector 3?
Yes, sir, we can use, sir.
What's the problem?
The problem is, sir, the difference between 1 and 2 will be less in comparison. The distance between the tip of the vector Bs and the tip of the vector of active vector 1 and 2 will be less in compared
Correct.
to vector 3.
This is the error you are talking about. Now here the error is not a scalar quantity. It is also a vector quantity. V error is basically what? V applied minus V actual, say Vs. Correct? So if you are realizing this vector using this V1 and V2, this is the kind of error vectors you are applying. V error is basically these two red lines, or maybe I can write in black. These are the error vectors. Whereas if you try to put 3, you will have error vector which will have so much magnitude. So of course we want to have lower value of voltage error when we are trying to realize even in per phase basis or in a vector form. Ultimate target is to have this voltage error being minimum or reduced. At least keep it low, if not minimized. So certainly 3 is out of question. If we want to keep it minimum, we must use 1 and 2 only for realization of this vector which is falling within this sector. Of course, if you want to use 6 for realization of this, we cannot use because this is beyond the boundary of 1 and 6. So 6 is out of question anyway. 5 is out of question anyway. 4 is out of question anyway. You understand my point? So only vectors which can be used for realization of a given voltage vector is basically which are within the or which are making the boundary of that particular sector where the voltage vector is lying. Thus, we must have the voltage vectors 1 and 2 for realization of this. Now, the next level, what I have been asking, yes, samples must be symmetrically placed. That is true. If you have only one sample to realize over here as the voltage vector and you keep it in the middle, say at 30 degree, you are kind of going to have V1 and V2 voltage errors almost equal. And the magnitude is like not very large. It is okay, can be considered. But if you try to have something over here at this location, your V1 may be small, but V2 will be very large. So what is the effect of these voltage errors? We will see tomorrow in the current analysis for the space vector. But because of this reason, we must have the samples placed in a symmetrical location within the sector or to a location from where the errors are not very large. It's kind of equally distributed. So yes, when we have just one sample, we can say that our gamma 1 is 30 degree. So gamma is something which is changing between 0 and 60 for each sector. So everywhere we can have sample which is located in the middle of the sector. Understanding my point? Is this clear?
Yes, sir.
Yes, sir.
Now the next question comes. If we have pulse number equals to 9, how would you decide the gamma? How would you decide the sampling angle? So first thing you also realize over here is that what is the angle between each sample? What is this angle?
60 degree.
60 degree. This is also called as something the sampling angle or sampling interval because time and angle are related through omega. So the gamma sampling is something which means that these vectors are repeating at every this angle gamma sample. And how much is that? It is basically 60° by number of samples, right? So P by 3 or n sample you can directly write over here. So for P equal to 3, what is the value of n sample? It is 1. So that's why we have gamma sample equals 60°, which means what? The samples are repeating at every 60°. So we are forming rules of this conventional space vector PWM, how to have these samples and then vector sequence and all that. Now, quickly, if we have P equals 9, how many samples should be there?
So 3.
So what is the gamma sample?
20.
Which means we should have 3 samples in each sector, and the angle between any 2 samples should be 20°, which means the rotating vector which is going on the circle, we are sampling it at every 20°. Every 20° you are clicking a photograph of that. Now where these samples should be? So 3 samples, let's say I am calling gamma 1, gamma 2, gamma 3. 3 sample locations will be there. Where should be now these samples located?
Sir, 10, 30, 50.
Why?
Sir, if we take like this, then it will maintain the symmetry.
That is okay. Maintain the symmetry. Again, I say symmetry can be maintained if you slightly change it here and there.
Sir, same thing like error can be minimized.
Yes. So you have to see in terms of extension of whatever we have done for P equals 3. Extension of this is P equals 9. Extension means you have one sample at the middle of the sector. So certainly this is always true. We need to keep one sample at the middle of the sector always. Now other 2 samples, which means gamma 2, we have deduced that it is 30°. Other 2 samples are located on both sides of this sample symmetrically. So if you fix this gamma 2 equals 30°, then what is the option for gamma 1, which means the sample which is coming in this half? So 20° apart, which means 10°. And what is the location for this sample? It is again 20° apart, which is 50°.
Sir, sir, I have a question. Sir, why we have every time have a sample at 30°? Symmetry can be maintained from 20, 40, and 60.
What did I say again here? Something we talked about voltage error, right?
Yes, sir. Sir, from 20, 40, and 60 can.
Listen again. We are keeping for pulse number 3, which means one sample in a sector, we are keeping at this location. Why? We want to have some reduced value of voltage error. Correct? If you keep anywhere else, one of the errors, either voltage error 1 or voltage error 2 will be more. Here it is kind of equal, almost equal. Correct? Same thing will happen if you try to keep with 20, 40 and 60. Here your voltage error 2 will be least, but voltage error 1 will be very large. Here your voltage error 1 will be, say, some low value, but voltage error 2 will be very large. And this is something which is having, again, kind of effect of both. Here if you see, if this one is having large value of voltage error 2, this will have large value of voltage error 1. But this is something balancing both. You understand my point?
Yes, sir.
So that is why we are extending the analysis what we did for P equals 1 or whatever understanding we have got for P equals 3, sorry. So the same understanding we are trying to extend for P equals 9. Do you understand this point?
Yes, sir. Now understood.
Okay. So now, once we have these angles, we can perhaps locate in the sector in a better manner. So what is happening? Say this is our sector 1. So what is the location? Certainly we have a sample located at gamma equals 30 degree. This is always there. And we have odd number of samples. So if one we are keeping at the middle of the sector, then others half we can keep on this side and other half we can keep on this side from the rest of the samples. So for P equals 3, one we are keeping at 10 degrees, say here, and another at 50 degrees, say here. Correct? So what's the angle between the two voltage samples?
20 degrees.
20. Even if you go for next sector, what will happen? Again, you will have next gamma coming at 10 degree. So you will have another 20 degree over here. Say for this next sector also here, the again gamma 1 would be 10 degree. So this will form a 20 degree gap between the two. So always this gamma sample is maintained for all the 6 sectors. Fine.
Yes, sir.
So if I generalize, say this is my gamma 2 for P equals 9, we are saying. If I generalize for any pulse number P, if I have n number of gamma to realize, I can say that gamma I is nothing but gamma sample by 2 plus gamma sample into I minus 1. This is the location of ith sample for a given pulse number. So pulse number will decide what is gamma sample. For example, or if you just simplify, this can also be written in terms of gamma sample I minus half. You can check if you put gamma sample equal to 60 degree, which means you have I value only 1. So which means this will come at 30 degree of the angle, which is pulse number 3 case. For pulse number 9, if you put, you will get angles gamma 1, gamma 2, gamma 3 as 10 degree, 30 degree, 50 degree. So this is kind of generalization of gamma. You can compute for any pulse number. Fine. So as an exercise you can take, you try to compute the sample locations for pulse number 15 and pulse number 21 using this. Either you can go by this, your understanding of the, the sector and how these are located, or directly this formula you can take. Understand my point? This is derived from this understanding only. Nothing else. One sample at the middle of the sector and then rest are located symmetrically around that. So certain rules we are framing over here regarding this sample is that no sample at the boundary of sector. We will not have any sample located at the boundary of the sector. All the samples are within the sector and those are symmetrically located. That's very important rule for conventional space vector PWM. Understanding my point?
Yes, sir.
Okay. Now, very common confusion which I saw last year, and maybe you also might be having. So let me ask simple question. Then we will move further to which vectors to apply and how to apply. Okay. Say we are realizing this sample. It is located at, say, first sample is there, so it must be at gamma sample by 2. Fine. From the formula you can put I equals 1 and that will become gamma sample equal to 2. This is gamma 1. Now the question is, how do we apply the voltage vectors 1, 2, 0 and 7 to realize this gamma? What is the meaning of we are applying these vectors to realize this sample? How do we apply? Where do we start applying the vectors? Where do we stop applying the vectors? We know that we are, let's say, following this sequence 0, 1 to 7, and we are dividing the 0 time equally and the T1, T2 what we have computed from our dual time computation. This is what we have. Where do we start applying? What is meaning of this Tz by 2? What is meaning of T1? Where does it start? You have to realize the sample at this location gamma 1. Where do you start? So this total time is, say, Ts. Ts is basically related to your gamma sample and it is nothing but omega into Ts. Say you can write T sample. Correct? Theta equals omega t, that's what is the simple thing. So all the other time durations here can be correlated with angle. Just multiply by omega. Correct? So how do we start applying? Where do we start applying these vectors?
0, 1 to 7 or other way around 7 to 1, 0. Like
other way around,
right?
but where do you start applying?
Like we
Where
will
would
start,
you start 0? At what point? At what time?
like initial
Or at what angle?
the start of carrier will be 0. Then after Tz by 2 we'll apply T1. Then
No, but
after
where would you start this? My question is that. At what point? Say my theta is rotating. Theta is basically the phase angle, right? Theta equals omega t, and from 0 degree it is starting and rotating continuously. This is going all the way up to 360. There is no problem in that.
90.
Okay, why 90?
Because we have to match with our peak, or basically we earlier explained theta is taken from 0.
No, that's not the point. It is something we are trying to realize this sample. Say this voltage vector Vs sample we have got over here. What is meaning of sample? If we have a sinusoidal waveform, you all have understood space vector from different sources and different classes also, but fundamental things, let's say, if we need to describe how we are doing what we are doing, there is problem actually. Let's say, what is meaning of sample? When we are sampling a sine wave, what is meaning of that? Meaning is that, let's say for this interval we have sampled. What we take a constant value of sine wave, even if the sine wave is varying slightly during this interval. We assume a fixed value of sine wave during this interval, even if my actual sine wave is basically changing from here to here. That's the meaning of sample, right? It is approximation of the sine wave, whatever it is changing from this point to this point, which is the actual thing, to just a constant value which is close by this value. Isn't it?
Sir, we can take like half the sample period that way, like on either sides.
Yes.
Like similar to in sine, how we realize a midpoint.
Correct. We are relating to that. We are correlating with our per phase basis. What we are doing, we are applying some positive and some negative. Effectively, what has happened? We have realized some average value. That's the meaning. That average value is realized if you are applying around this. So now here it's only magnitude. So confusion is not there. You apply for, say, t on time this positive and t of time this negative value, and you are getting the number which is average of the two. Fine. In the scalar terms, there is no problem. But in vector, in terms of vector, what we have basically, we have to apply the vector such that the average of all these vectors or all this volt second is basically what is given by this sampled vector Vs into the sampling time Ts. Do you understand this point or not? Say, simple terms if I tell, if I start applying my vector at this point, I start with 0, I applied 0 for tz by 2, then I went to 1, I applied for t1, applied vector 2 for time t2, and then I applied v7 for time tz by 2. By that time I have completed this much duration or this much angle, right?
Yes, sir.
Are you listening what I am saying?
Yes,
Yes.
sir.
All of you?
Yes, sir.
Okay. Time is related to angle. This you have understood? Do you have this understanding? Time is related to angle?
Yes, sir.
Okay. So if I say that I'm applying these vectors for this much duration, what will happen to my actual vector which is rotating continuously? It will complete the path or the journey from this point to this point. Isn't it? During this interval, my actual voltage vector will be moving from this point to this point. Fine?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. And we say that this vector what I have drawn over here is basically sampled version of the vector which is rotating from here to here. Correct? This is approximation of what is rotating from here to here. This point, do you understand?
Yes, sir.
Correct? Which means while this vector is rotating from here to here, when we are applying these vectors for these durations, effectively we are balancing or we are kind of realizing what should have been in the middle of the sample or in the middle of this complete duration, isn't it?
Yes, sir.
Correlate with this. We have to realize something for this duration, say Ts by 2, and what we are doing, we are applying something and something for this complete duration, and we have realized the average value here. Is the actual voltage like this here? How is the actual voltage? Actual voltage might be changing like this.
Yes, sir.
Okay, are you able to correlate these two things?
Yes, sir.
Think about it again. Okay, I leave this whatever description I have given over here to you to know for thinking on it little bit more, and then you come back tomorrow with your understanding what you have understood by this point. What I'm trying to say that if you have to realize a voltage vector at this location gamma sample by 2 or at any location, you need to basically apply the voltage vector symmetrically around this. So if you start applying from this point up to this point your vectors in this manner, actually you will be realizing what is located in the middle of this on an average basis. Just think about this statement again, and tomorrow we will discuss on this little bit more, right?
Yes, sir.
Yes or no?
Yes,
Yes,
sir.
sir.
Sir, and
Yes, sir.
and the like the hexagon also, like in some of the books they take the reference vector as like per phase basis. The reference vector they multiply with 2 by 3.
I will come to that. Don't worry. I'll come to that. How to realize the voltage vector from the per phase value or per phase magnitude. I will come to that.
Yes.
But in effect, we are trying to have over here is the cumulative effect of all the three phases, not just individual. Okay, but yes, of course, this Vs can be correlated with the per phase peak value. That I will come. Don't worry. Okay.
Sir,
Is
and
this
one more confusion was regarding the sample time period. Like in other course, we were taught like sample time period will be simply twice, it will be half of the actual like the frequency time period. So we
Which
just took two samples.
No, which frequency you are talking about?
Switching frequency, like the switching time period.
That is also true. See what we do over here in case of sine triangle PWM. We have the triangular carrier, right? Where are we sampling? We are sampling here and here.
Yes, sir. In that way, like, sir.
So it is the same thing. Now, if you think closely, here also we are doing the same thing. How? Each sample or each this sub-cycle I have said no is basically representing what? One of the sequences 0127 or 7210. Basically, this will be 7210. This will be 0127. So, which means what? Basically, I am talking about one sample which is equivalent of one sub-cycle in the carrier.
Okay, so this is for only one single sample per sector, like this one.
This is true for all the samples, for all the pulse numbers.
Sir, then we'll get multiple. Okay, sir, I'll just go through it.
Check again. That's why more than what I teach, no, you need to think and grasp it on your own.
But sir, this is double sampling, na?
Which one?
Whatever, like in each subsection, if we take two samples, then it is double sampling. Like if you.
It is double sampling. The sampling is what basically we are doing at the peak and valley of the carrier. Correct? Now, each sample we have correlated with the space vector that it is kind of applying either of the sequences. And from here we went on to say that conventional space vector PWM is nothing but we try to have one of these sequences for realization of the voltage vector in one sample. Correct?
Yes, sir.
Now are you able to correlate this? It is the same thing. It's not different. So from here, if you compute, how would you determine how many samples should be there? Again, you go back through the same analysis what we have done. You will find that ultimately you should have P by 3 number of samples within one sector. And this is on basis of we are sampling at every peak and valley of the carrier. Or we are having the realization on basis of each sub-cycle. Understanding my point? You have to ask questions. This is a very important time when you should ask questions. Okay, here because there is no one flow of teaching this. Few things I will tell, but more than that, if you want to understand, you need to ask. Based on what you know or what confusion you are getting, you need to ask more and more questions. Is it fine, Shambhunath?
Yes, sir. Yes.
Okay. Any more questions here? I need to stop because you have next class, right? So tomorrow again we will see how whatever confusions you have here, you ask why it is coming like this. Just think about it a little bit more. The statement remains the same. Think about it a little bit more and then come up with the confusion what you are having. That's the point. Then we will go by checking, can one sequence be applicable everywhere, or we need to change something, or something else should be applied, how to go from one sector to another sector. These things we will try to see, and how to generalize this. Let's say whatever analysis we do for sector 1 can we say that it is applicable for all? How to get that understanding? These kind of things we will see tomorrow with some more analysis on the current ripple and equivalence with the sine triangles. Fine. But before that, just think and do on your own whatever things I have described over here. Correct?
Yes, sir.
Yes,
Okay. Let's stop over here.